Hello everyone, this is the worksheet 11 video key. All right, we start out by talking about nucleophiles and electrophiles. So just a reminder, nucleophiles are the electron-rich components that are attracted towards the positively charged nucleus of an atom. Electrophiles are electron-poor atoms that can accept electrons from other atoms. So here are some examples in this summary. Let's go ahead and see if we can put that knowledge into action here. And it says, do you expect the reactants below to act as nucleophiles or electrophiles? Label all the electrophilic and nucleophilic sites on the following molecules. So we're going to start here with this alkyl bromide. And so you might have recognized that there is a bond dipole that exists between a carbon-bromine bond, and specifically making this carbon have a delta positive, right? And because it's a delta positive, it is an electrophilic site. Some people might label the bromine, which does have a slight negative, as a nucleophilic site. However, I'm going to refrain from doing that just because right now bromine is already making one bond. And remember that bromine, unless it's going to expand its octet, which typically doesn't happen in organic chemistry, it is not likely to make a second bond. So while it's currently attached to a carbon, it is not very nucleophilic. If you compare and contrast that to, for example, bromide, right? So bromide would be nucleophilic. It has a full negative charge, so it's electron rich, and it's making bond, and it can donate a pair of electrons to something that's positively charged to make that bond. What's considered nucleophilic. But right now, while it's attached, right, to the carbon, it is not. And that stands for like chlorine and iodine as well. Okay, moving on. So I would expect this one to primarily be electrophilic. Looking at this structure with the oxygen with a formal negative charge, we see that having an atom with a negative charge, right, should hopefully immediately tell us that this molecule is likely to act as a nucleophile. And specifically though, right, it's the oxygen itself that has the full negative charge in this case, that's likely to be the nucleophilic atom. Let's look at this carbocation, right? Hopefully that positive charge shows you that if we have a structure that has a delta positive, meaning a partial positive charge, and that's electrophilic, right? Then something with a full positive charge would be even more so expected to be electrophilic. Okay, so we'll go ahead and label that as electrophilic. Right, and this is, I guess I should have been writing electrophile, nucleophile, and again, the whole thing is called an electrophile, even though the carbon itself is electrophilic. Okay, so it does tell us to consider resonance. And as we start looking at these bottom structures, resonance is going to be important here. So if we think about the resonance contributors of this structure, that's actually really critical to understanding the electrophilic centers. So let's draw that out. We have this structure, and we can do pi bond between atoms of differing electronegativity. Which moves the positive charge down to this carbon. And then we can actually keep going and do the allylic positive charge pattern. Which actually moves that charge even further down, right? So really, the nitrogen and the two carbons all share the positive charge. So they could all be considered all electrophilic centers, right? But I am actually going to primarily label the carbons as the electrophilic centers. And that's because if you think about it, right, which is the most significant resonance structure here? Hopefully you all answered this one. And the reason for that is because these two lack an octet at the carbon, right? So, and remember that the carbons that lack an octet are particularly unstable, right, with that positive charge. So nucleophiles typically will react with those to help satisfy the instability of the positive charge at that carbon. So it would not be wrong, though, if you also included the nitrogen as well as one of the electrophilic centers. We'll write electrophile here. Here we have another positive charge, a full positive charge, which kind of gives it away that it's going to be an electrophile. We didn't even have to look for partial charges when they give us a full charge. So let's go ahead and look at the resonance contributors for that question. In this case, we actually just have two resonance contributors that are related by the allylic carbocation pattern, right? So the electrophilic carbons are not just the one that's shown here, right, which is this one, but also resonance shows us that this last carbon as well is also electrophilic, right? And so that's really important because nucleophiles could attack either one of these carbons. They actually share the positive charge, which is not indicated if you just look at one structure. Okay, this one with the full negative charge hopefully gives it away that it's going to be the nucleophile. And if we think about the resonance structures from that case, we are going to move it up. Now we're going to use the allylic lone pair pattern. Right, and then this shows us that the negative charge is shared between the oxygen and the carbon. So both of these, both the oxygen and this carbon are nucleophilic. And if you did not draw out resonance structures, probably couldn't have come up with the fact that this one is nucleophilic with a partial negative charge. What about our last example here? This one's very similar to the last case, but instead of having a full negative charge, right, we have a partial, we'll end up having partial charges. So we're still going to do the same pattern, the allylic lone pair pattern. Right, and so that actually shows us that there's a partial positive charge on the oxygen and a partial negative charge here. And one thing that you don't necessarily know yet, but when you have oxygen or nitrogen with a positive charge, typically those atoms are not attacked directly by a nucleophile. Instead of that, they're usually attacked at the carbon attached are double bonded to the oxygen or nitrogen with a positive charge. Right? So it's actually really the carbon here that is nucleophilic. Right? And so we're going to write nucleophile. Okay. And hopefully it's not too confusing. I know some people would have probably circled the whole pi bond, right? But so for example, if I had given an example like this, right, then you would have, you can circle the whole thing and say, right, that these two carbons are both nucleophilic. And that's because they're essentially equivalent in an alkene. But in a case where there's resonance, right, both of these carbons are not equally nucleophilic. Instead, resonance shows us that this one is much more nucleophilic than the other. Right? So we're not going to circle the whole pi bond in this case, specifically focus on the one that we know has the partial negative charge. Okay. Moving on to the next section here. This one is just a review of the different patterns of arrow pushing and polar reactions. We are going to be labeling steps as nucleophilic attack, loss of a leaving group, proton transfer, or rearrangement, specifically, or more specifically, a carbocation rearrangement. Let's go ahead and use those to help us not only label the steps, but also to draw in the curved arrows. So what we have to do is look and see what happened here, right, in order to be able to know how to draw the curved arrows to get to this intermediate. So what I'm seeing is that there appears to be a bond being formed between this carbon and the nitrogen, and that the oxygen, right, which now has two lone pairs, is going to end up losing its pi bond and getting a third lone pair. So what we can do is have the nitrogen's lone pair do a nucleophilic attack, combine this with a resonance arrow, right? And we can call this nucleophilic attack. Right? So technically only this arrow is the nucleophilic attack, but in order to avoid exceeding the octet on this carbon, we also needed another arrow, which is just a resonance arrow, to help us move electrons simultaneously away from the carbon and onto the oxygen. And then between here and here, what looks like what we've changed is that the negatively charged oxygen has gained a proton. This is going to be a proton transfer. Right, and we can show a proton transfer. That's probably the one that's the easiest for you because you've had lots of practice with chapter 3. Right, we're going to do our two arrows where the base takes the proton from the acid and the acid keeps its lone pair. Okay, from here to here, we need to see what's changed, right? It looks like one of these protons has been removed from the nitrogen atom. So this could act as a base. It could come in and take this proton, leave the electrons behind, and we have another proton transfer. And then from here to here, it looks like the oxygen is now gaining another proton. We have a third in a row now proton transfer. Now it looks like water is being expelled, right? And we are forming a double bond between the carbon and nitrogen. We can show loss of a leaving group, right? And simultaneously show the resonance arrow to form the carbon-nitrogen double bond. And I actually might even write that in for you. I'm just going to write and a resonance arrow, just so it's really clear. You don't have to write that if you're just asked for one of the patterns, just for your learning process. I want to make sure you understand that this arrow is the resonance arrow. And over here, this arrow, right, is a resonance arrow. Okay, and then lastly, looks like we are losing this proton. Water can act as a base and come in and take that proton, or they've actually drawn this sort of generic A base that we can use. So we see that it does pick up the proton to become the conjugate acid here. Right, so another proton transfer. Maybe I should have even made the resonance arrow blue, right? So it's really clear which one is the resonance arrow. Okay. Moving on to the next one. The transformation here appears to be proton transfer. We're going to write that in. We'll draw that proton transfer. Arrows. And then it looks like water is going to do a nucleophilic attack here to make another carbon-oxygen double bond. And we will have a resonance arrow to move electrons up to the oxygen. Right, so let's draw the resonance arrow in a different color. This one is the resonance arrow. That will place the positive charge here. And then water will be able to do a nucleophilic attack on that carbon. We're going to call this a nucleophilic attack. And then I'm going to write and a resonance arrow. Okay, from here to here, it looks like we are going to lose one of these protons, and water will be the base, and it'll form hydronium ion. This is going to be a proton transfer. I can go ahead and draw in those lone pairs since water is going to be the base. And it will take one of the protons off that oxygen. Those are the two proton transfer arrows. And then here, right, the nitrogen becomes protonated, right, with a third hydrogen atom. So we can show again another proton transfer. And then we have a proton, so we're going to be kicking out the NH3 group, because you can see it's separated from the molecule here, and we'll be reforming a double bond between one of the carbon oxygens. So since this is getting kicked out, right, we can show it leaving the molecule, right? So we call that a loss of the leaving group. And then I'll just write the wrong color. Okay, I can just use another color. Dark blue. So this one will be, and again, from any one of those four lone pairs is okay, right? And I'll just write and a resonance arrow. Okay, and then lastly, the oxygen here will be losing that proton. So we have another proton transfer. So base takes the proton from the acid, leave the electrons behind as, oh, Sorry, taking the wrong proton. Come over here and take this proton, so we can form this product. Okay. Moving on to the next one here. We have, it's like the first step is a proton transfer. We need to show the curved arrows for that. And then it looks like we have a new bond being formed. So this is going to be a nucleophilic attack. And then we'll show the arrows for that. So it looks like the oxygen is going to be bonded to the carbon. So this is the delta negative oxygen attacking the delta positive carbon here. You know it's delta positive through resonance. So that is the nucleophilic attack arrow. And then we'll also write and a resonance arrow. From here to here, we have lost a proton, so this will be another proton transfer. Let's go ahead and draw the arrows for that. And then from here to here, we have another proton transfer. Looks like we are losing water in this step, so this will be loss of a leaving group. Both nucleophilic attacks and loss of a leaving group steps also commonly involve a resonance arrow. And so what we'll see here is that this is the arrow for loss of a leaving group, but we also need our resonance arrow. Right, and so over here I'll write and a resonance arrow. Okay, looking from here to here, we see what's changed. And it looks like the methanol is now going to be incorporated into the molecule. This will be a nucleophilic attack. Remember, those commonly also involve a resonance arrow. The actual nucleophilic attack is that arrow, right? And then we also have electrons moving up from the pi bond to the oxygen. So we'll say, and a resonance arrow. Ugly looking arrow, but sorry about that. Then lastly, a final proton transfer. And we have a nice space here that can come in and take the proton away. Okay. Moving on to the next page. Carbocation rearrangements. Starting with carbocation stability. Classify the following carbocation as primary, secondary, or tertiary. So this one is primary, right? And by the way, when we get into chapter 7, we'll talk a lot about the fact that primary carbocations are actually too unstable to form. This is so unstable, we would never actually form that in a reaction, but that information will come back and again become important more in chapter 7. This is a secondary carbocation because the carbon with the positive charge has 2 carbons attached. This one has 3 carbons attached, so it's tertiary. This one only has one carbon attached, so it is primary again. Remember, too unstable to form in reality. The earlier you learn that, the easier it will be. Chapter 7. This one is secondary. Again, primary, but this one is kind of special, right? Because this one is not just primary. You might think, oh, primary, really, really unstable, right? But this one is primary, and we'll say, and allylic, right? So it's actually a lot more stable than it looks because of the resonance stabilization. This carbon is tertiary. And then just to note that sp2 hybridized carbocations are also very, very high energy, and they don't form, just like primary carbocations don't form. Okay. Which of the following is more stable? I.e., lower in potential energy? Explain your choice. Right? So this one is actually more stable. Right? And due to resonance stabilization. Right? So this one is a tertiary carbocation that's localized. This one is also a tertiary carbocation, but remember, it's more stable because this carbon doesn't have a full positive charge, and instead the positive charge is delocalized onto two different carbons. Therefore, each carbon only has to have a partial positive charge, which is more stable. So just to remind you what that resonance stabilization would look like, do the allylic carbocation or allylic positive charge pattern. Okay, and so we'll then, we can also write more. We could even say the positive charge is delocalized, as well as the electrons. Right, whereas again over here, the positive charge is localized on just that one carbon. All right, number 5, rank the following carbocation in the order of increasing stability, with 5 being the most stable. Right, so let's look and see. First, we might want to categorize these. Okay, this one is primary, this one is secondary, tertiary. This is what we call vinylic. Remember, those are particularly unstable. And then this one is both tertiary and allylic. Right, so if I label these, so with A, B, right, so we'll have from least stable. I guess I should have done it 1, 2, 3, 4, 5. Okay, so we'll just change that to a bit weird the way I've done my ranking, because I've sort of just labeled them like this. I have to change it based on the way the question is asked. I actually do need to go in and just write 1, 2, 3, 4, 5, but not randomly. To start with the least stable and then move up to the most stable. So the least stable is definitely vinylic, followed by primary, secondary, and tertiary, and then tertiary and allylic being the most stable. Okay. And then this one talks about how carbocations only rearrange to produce a more stable carbocation. Right, so if we're looking at this, we recognize this is secondary. So it would only rearrange if it could become tertiary or allylic. Those are the conditions. So if you want to figure out what possibly shift could occur to make it more stable, you can think about this as being the alpha carbon, or carbon number 1, and the carbons attached are the beta carbons, or you might label them like they did, carbon number 2. And then you think about all the different groups that are attached here. Okay, we've got 3 hydrogens on the right and a methyl and a hydrogen on the left. So any of those could potentially shift over to form a different carbocation. But again, it's only going to happen if it makes it more stable. So first they analyze, what if one of these 3 hydrogens shifted over? If that was the case, what was secondary would become primary, and that's not more stable. That won't happen. What if this methyl group shifted over? Right, that would be called a methide shift. If that happens, then we would end up with a secondary benzylic carbocation, which actually is pretty good because it's pretty stable, right? But it's not the most stable carbocation. If you end up shifting the hydride over from the carbon on the left, you end up with tertiary and benzylic. And that's the most stable carbocation we possibly can get. So that would be the correct shift. Let's go ahead and practice that skill right here. These problems. So this is a secondary carbocation, which means it might rearrange if it could become more stable. But all we have are 3 hydrogens on here, which if they shift over, this would become a primary carbocation, so that won't happen. You could potentially shift one of the hydrogens on the left. That would again be another secondary carbocation, so that would not make it more stable. And some of you might even think, what if can I shift this whole ethyl group? It's not common because it's a little bit more bulky, but it can happen. But if you did, again, you would get a primary carbocation. So that's not likely, right? So this one will not rearrange because you cannot form a more stable carbocation. Right? So we'll just do it next. Okay, what about this one? So I do want to remind you, right, because again, this whole course is cumulative, that even though we're drawing this right now, right, a primary carbocation, in reality, you're not going to see that in an actual reaction mechanism because primary carbocations are too unstable to form, right? So this is kind of, we'll put like brackets around it, like a theoretical structure, not a structure that can actually exist. Okay, so if it could exist though, right, can we potentially do a rearrangement? Right? Well, there's no carbon to the right, but there is this carbon to the left, and there is a hydrogen here that we can shift over. Right, so that's a hydride shift. And if that happens, we would end up with a tertiary carbocation. Right? So what was primary now tertiary, right? So yes, this definitely shifts. Again, this is a hydride shift, which is one of the possible types of carbocation rearrangement. Okay, moving on to this structure here. Right now we have a secondary carbocation. So we ask ourselves, what if we remove one of these hydrogens over here and shifted it over? Then it would still be secondary. However, there is a hydride and a methyl on the right. The methyl shifts over, it would still be secondary. But if the hydride shifts over, right, then would end up with a tertiary carbocation. So that can occur. And recall that shifts can only occur from adjacent carbons. Okay, I actually just want to write it in. Primary carbocations are too unstable to form. Okay, just so it's really clear. All right, what about this? Right now, this is a tertiary carbocation. We could think about a shift, but unless it's going to become allylic, then it's not going to shift, right? Because everything is not as stable as tertiary except for a resonance stabilized carbocation. So this one, there's no way we can get it to anything more stable, right? So this one actually will not rearrange. This one, yes, it will rearrange. Okay, so primary goes to tertiary. This one we had secondary go to tertiary. All right, moving on. We have a secondary carbocation. We might think about doing a shift, but we would actually want to shift probably one of these hydrogens on the left, because while it will still give us a secondary carbocation, it will end up being resonance stabilized into the ring. We call that benzylic. Right, so this hydride shift gives us the carbocation on the carbon directly adjacent to the ring. Right, so this one is considered secondary and benzylic, right, which has resonance stabilization. Definitely this one. Right? Secondary to secondary allylic. Yes, it will rearrange. Okay, so this one's actually tricky. I'll come back to it at the end. We'll go ahead and go and do this one next. It kind of looks very similar to that anyway. So we have a secondary carbocation. And so let's think about how we might be able to get a shift going here. There aren't any hydrogens to potentially do a hydride shift. However, we could do a methide shift, right? This one is called a methide shift. Which turned our secondary carbocation into, again, secondary and benzylic. So definitely that's more stable. Sorry, I actually noticed I wrote allylic up here, but this is benzylic. Benzylic. I want to write that again. Okay, moving on to this one. Right now it is tertiary. And again, tertiary we only really rearrange if it can become allylic, which it cannot, right? So this one will not rearrange. So here, this is secondary and allylic. Right, so there is no shift, there's no hydrogens over here to shift on this side, and these would make it not allylic. This one will definitely not rearrange. Let's look at this one. This is also secondary, right? And if we do a hydride shift, we can get it to an allylic position. That was definitely favorable. We can go ahead and draw at least one of those hydrogens in and draw that arrow to show it shifting over. But if you want, you can draw the hydrogen that shifted over here, but remember that in a line structure, you don't have to draw those. Okay, so it's shifted, and now this has 4 bonds total. Right, so now we have secondary allylic. Right, so definitely this one will shift. Secondary to secondary allylic, and it will rearrange. Okay, let's look at the questions on the bottom here. This one is secondary. Right, if we were to move any of these hydrogens over, it would be primary. If we were to move one of these 2 hydrogens over, it would still be secondary. So there's no driving force. And you might be thinking, well, maybe I can just have this methide shift over. But recall that this is too far away. If there's going to be a hydride or a methide shift, they have to come from one of the adjacent carbons. Okay, so this one will not rearrange. And then over here, we have a tertiary. And again, the tertiary carbocation will only rearrange if it can become allylic. But recall, there's only time for one shift. So we can't like shift one and shift another one so it becomes allylic, right? So if you can't get it allylic in one shift from a neighboring carbon's hydride or methide shift, then it will not rearrange, right? So in order for this to get over here and be allylic, it would require 2 shifts, and there's just not time for that, right? So this one will not rearrange. All right, let's go back up to the one that I said was tricky up here. And let's classify it. So this is a secondary carbocation. So this one is tricky because you might think to yourself, I can do a hydride shift, right? If I draw in the hydrogen here, then I can shift it over and it will become tertiary. And that is in fact more stable, right? But that's actually not the way to get the most stable carbocation. And the reason for that is because right now, this 4-membered ring, which has a lot of ring strain, makes this whole molecule not stable at all. What we can actually do is what's called a ring expansion. We can take one of these 2 carbons that are in the ring and shift it over. So for example, I can do what's sort of equivalent to a methyl or methide shift, except for it's not a methyl because it's part of a ring, right? But it's still a carbon anion that's shifting. But the key here is that when this occurs, right, we end up with a 5-member ring. When we have this ring expansion, right, we end up with this 5-member ring, and there'll be a methyl, right, still attached to this carbon. And then this carbon, which is right next to the carbon then with the methyl, will end up positively charged. You could either draw that here or here. Right? And a lot of people have trouble kind of seeing what that might look like. Right? So what I can do is maybe try to show it to you with partial bonds, sometimes helpful. Right? So we have something like this. And then what we're going to do is start to, right, we'll sort of say this bond starts to break. And then this bond starts to shift over to here. Right? So we have a bond, this one here, right, just starting to break. This one is starting to form. So on your paper, if you were using pencil, right, you could almost erase this bond and then draw it over here, and then you'll see that you have a 1, 2, 3, 4, 5-member ring. You do that. That this carbon, since it's losing the electrons from this bond, is the one that ends up positively charged, which is right next to the carbon that ends up with the methyl group. Right? So this one is a little bit of an advanced topic, but I wanted to go ahead and show it to you guys right now anyway. Right? So this is actually called a ring expansion. Right? And it's sort of the equivalent to a methide. Maybe you might actually call it a carbide in this case. Shift. And so this happens because now we have a 5-membered ring, which is more stable than a 4-membered ring. And that would actually still be more stable than the 4-membered ring with the tertiary carbocation. Because remember how unstable 4-membered rings are, right? We learned about that in chapter 4. Right, we'll stop there. You guys have a good